In this lecture, we will start discussing about the mathematical classification of partial differential equations and their physical behavior. We know that in fluid dynamics, aerodynamics, we handle a large number of partial differential equations, and therefore, we need to have a more in-depth understanding of their behavior, both mathematical as well as physical. In terms of classification, there are three broad categories in which we can distribute them: elliptic, parabolic and hyperbolic. And why we try to classify them this way is because when we start developing numerical schemes to approximate them and solve them in computational aerodynamics or computational fluid dynamics, we have to devise numerical schemes which are appropriate to each type of partial differential equation. So, until and unless we classify them and we understand their mathematical behavior, an appropriate numerical scheme will not be possible to devise in order to undertake the approximation or the discretization of the partial differential equations. We also need to understand the physical basis, so that we know that physically how do they behave, how do the solutions behave, what kind of solutions each type of partial differential equation can accommodate. So, that is basically the motivation behind this discussion. We are considering a partial differential equation which is in phi, where phi is a function of x and y, and we have a second order partial differential equation in phi, in the sense that the highest order derivative of phi here is 2. So, you have a second order partial derivative of phi with respect to x, with respect to y. This is a mixed derivative in both x and y. So, these are all second order derivatives. These are followed by first order derivatives, followed by the variable phi as well as a constant term k. So, this entire expression equates to 0. So, this is the partial differential equation that we have in hand. When we classify this partial differential equation to one of those three categories, the first important thing that we have to keep in mind is that we only consider the second order derivatives while we do this categorization. We have seen that there are coefficients associated with each one of those terms, whether second order derivative or first order derivative or the phi term. There are so many constants associated or coefficients associated. So, when we categorize, since only second order derivatives are important, we bunch all the first order derivatives, the variable term and the constant term together, and then they are sent to the right hand side of the equation. So, this term S, it actually accounts for all these terms when taken to the right hand side. Of course, the signs of those terms will become negative. So, that overall gives you the S. As far as the second order terms are concerned, we have to take note of their coefficients A, B and C. They are going to play a pivotal role in the classification process. Now, if we go into the mathematics of this approach, we will find that the value of b square minus 4 ac which can be identified as a discriminant, will help in the classification. How does it help? When this term b square minus 4 ac is greater than 0, we say that the equation is hyperbolic, where there are two real characteristics. What does that mean? Characteristics, we need to note, are paths through which information is propagated in the solution domain. So, we have to interpret characteristics in this way, that if there are real characteristics coming from a hyperbolic kind of partial differential equation, then there are real paths along which information will propagate through the solution domain. We will be able to identify those paths. When it becomes equal to 0, we have a parabolic partial differential equation, where instead of 2 there is only one real characteristic. So, there is still one path along which information can propagate. When it becomes less than 0, then it becomes an elliptic partial differential equation, and there are no characteristics or no real characteristics, so to say. That means, there are no paths or directions along which information can propagate. So, what is going to be the implication? We will see in due course. Now, if you try to look at the problem from an application perspective, when it comes to fluid dynamic equations, especially in aerodynamics, we are often concerned with a range of velocities. Sometimes we are talking about low speeds, it could be incompressible flow, and therefore, the Mach number is typically approximated to 0. But then there could be situations where the flow is compressible, and then we are concerned about the Mach number of the flow. So, when the flow is inviscid in nature, then a subsonic Mach number flow, when it is of a steady kind, you may recall that the time derivative terms in such equations go to 0, then the equations behave in an elliptic manner. That means, there are no real characteristics, there are no directions along which information can propagate. Probably information will propagate along all possible directions, we will see later. And then in supersonic conditions, it becomes hyperbolic, that means, it has real characteristics, 2 of them typically for an equation of this kind. And when we deal with the inviscid equations in an unsteady manner, irrespective of whether it is subsonic or supersonic, the nature is hyperbolic. When it is viscous equations, we see on the contrary that the steady form behaves in an elliptic manner and unsteady form behaves in a parabolic manner. So, depending on the kind of equations that we are handling, there are differences in the way the fluid dynamic equations behave, and therefore, obviously, when we talk about numerical schemes in computational aerodynamics, then the numerical schemes will differ. Just as an example, we are citing a governing partial differential equation of second order in phi, where phi is the velocity potential. And what equation is this? We are familiar with the velocity potential equation or the full potential equation, which we had derived earlier. So, if you apply it in a steady 2-dimensional form, then this is how it will look like in the xy plane. So, we are talking about steady isentropic inviscid compressible flow past a slender body, which is essentially a small disturbance source or a small perturbation source. So, this equation models such flows, and going by what we learnt in the earlier slide, we have to identify the coefficients of the partial derivatives. So, there are partial derivatives in x and y only in this equation, there are no mixed derivatives. So, we can easily identify the values of a, b and c, based on which we can work out b square minus 4 a c, which turns out to be this. Now, we have to see that for subsonic conditions what it works out to be. We find that this is less than 0, which means the behavior will be elliptic. When you go to supersonic conditions, on the other hand, this becomes greater than 0 and therefore, it will be hyperbolic. So, here you will have no real characteristics, while in the other at supersonic conditions you will have 2 real characteristics. The question may arise in your mind that what would happen at m infinity equal to 1. Incidentally, if you go close enough to m infinity, this equation will not remain valid, because it is not going to model such a flow. The flow becomes extremely non-linear under such conditions in the transonic regime, and therefore, this equation is not appropriate to model such flow. Therefore, we will not try to analyze this case, since this equation loses its validity. Let us do a little more discussion on what we mean by characteristics and how does it show up in the solution sense. So, we are looking at hyperbolic equation. In hyperbolic equation, you can look at the problem in this manner, that you have a x t plane. So, this is the spatial domain spanning from x equal to 0 to x equal to L, and then the time proceeds from t equal to 0 to infinity. You can see 2 characteristic lines, which are the real characteristics we have been talking about. And if you are looking at a point P, which has coordinates x t in this plane, at which you are trying to obtain the solution of the governing hyperbolic equation, then you find that these characteristics are defining a so called domain of dependence, which is propagating information into that point, and the solution at that point is dependent on this domain of dependence. Further, the solution at that point P can influence a region which is called as zone of influence. Remember that these slanting characteristics basically mean that the information propagation is happening at finite velocities, because these characteristics are associated with finite values of dx dt. When you go to parabolic equations, this is how the solution domain would look like. If you are interested to work out what is happening at this point P, then you find that there is one real characteristic, and that basically defines the domain of dependence of this point P, and this real characteristic is parallel to the x axis, which means that the disturbances can propagate at infinite speeds. They do not need any time to propagate to that point, unlike what it was in the case of hyperbolic equation. And the solution, of course, will proceed along the time direction and also span across the spatial direction. When it comes to elliptic equations, how does it look like? We have first of all a closed domain, and then if you are looking at that point p x t, since there are no real characteristics, informations travel from all directions first of all, and they travel at infinite velocities. There is no time delay for the disturbances or informations to propagate to that point and influence that point. Therefore, the entire region is the region of dependence or domain of dependence, which influences that point. we discussed about the solution domains of hyperbolic, parabolic and elliptic partial differential equations. Now, we are also going to look at two categories of physical behavior. So, what are they? We will find that these three different categories fit into one of them, either equilibrium problems or marching problems, and then we will also try to understand what we mean by them. First, let us discuss about equilibrium problems, and of course, you may recall that what we are seeing here, this figure pertains to elliptic equations. Now, equilibrium problems, these are steady state problems, which basically means the time dependence is not there. Laplace equation and steady state conductive heat transfer equations are examples of this category, and they belong to elliptic partial differential equations. Now, these are boundary value problems. As we said that the entire domain is bounded. So, this is essentially the boundary of the domain, and you have to impose boundary conditions all along the boundary when you solve this problem. An important feature of elliptic problems is that disturbance in the interior of the solution domain affects and alters the solution everywhere. That means, there is no zone which can be identified as that of dependence or influence. These work in the case of hyperbolic equation or parabolic equation. Here, it is the entire domain which is influencing. Also, the disturbance signals travel in all directions through the interior solution at infinite velocity, and therefore, what happens is that the solution of elliptic partial differential equations, they are always smooth. Even if the boundary conditions are discontinuous, the inner solution domain is always going to yield a smooth solution. Again, to ensure that information propagates in all directions, the numerical techniques that we devise for elliptic partial differential equations, they must allow events at each point to be influenced by all its neighbors. Therefore, the interpretation in the numerical techniques should be consistent. You have a physical behavior of the partial differential equation, which has to be correctly reflected in the numerics. Just to cite an example, earlier when we were discussing about panel method, we calculated the velocity potential at a panel control point. While we did it, we accounted for the effect of all other singularities in the domain. That means, influence is coming from all corners of the domain. In the panel technique, it is the distribution of singularities on the body as well as in the free stream, but all the influencing factors are coming in order to calculate the velocity potential at a panel control point. So, that is typically the strategy followed for solving elliptic partial differential equation, and why we did it over there was because we were solving Laplace equation through the use of those singularities. Let us move on to the next category, which we are calling as the marching problems. So, which kind of problems come under this category? Transient heat transfer, that means unsteady heat transfer. Any kind of unsteady flow, that means time dependent flow, wave propagation phenomena, These are considered as marching or propagation problems. And what are the partial differential equations which help us to model them? Of course, you can now guess the remaining two, parabolic and hyperbolic equations, both fall in this category. And when you are talking about a flow problem, then the flow direction acts as a time-like coordinate along which marching is possible. So, you remember that the behavior of the parabolic partial differential equation, or for that matter for all the three categories, were shown in the x t plane, where time was interpreted as the marching coordinate. However, there may be problems where the flow direction acts as a time-like coordinate along which marching is possible. So, instead of marching along time, you may be also marching along a particular flow direction. Example of unsteady flow can be imagined this way. Let us say you have a channel within which you have a stagnant viscous fluid, and then at t equal to 0 plus, that means a small instant after t equal to 0, you suddenly move this upper plate with some velocity. Because it is a viscous flow, the flow cannot slip here on the upper surface, and therefore, along with the wall, all the fluid particles which are adjacent to that wall also start moving with velocity u infinity. And after a while, you will find that momentum will percolate from the moving fluid to lower layers like this. And finally, after a long time, the velocity distribution may look like this. So, the final steady state solution may look more like this. The velocity distribution across the channel height may look like this. So, this is a typical unsteady flow problem, because the problem has a time dependence. So, only when the steady state is reached are you saying that asymptotically the time dependence will go to 0. So, this would qualify as a parabolic partial differential equation. We can show that. So, parabolic equations describe time dependent problems which involve significant amounts of diffusion. So, we were talking about momentum diffusion here. Similarly, in thermal problems, when we talk about transient heat transfer, you can show that because heat can move from one end to the other of a conducting medium, you may have a time dependent temperature distribution in that medium. So, unsteady viscous flows and unsteady heat conduction therefore become examples of this category. Mathematically, it is going to be an initial boundary value problem, like we saw over here, that there is an initial condition from where the whole problem starts evolving, and it evolves based on certain boundary conditions which you set at the lower and upper walls. Therefore, it is an initial as well as boundary value problem. When you look at disturbances, the disturbance at a point in the interior or boundary of the solution region can only influence events at later times. The solutions move forward in time and diffuse in space. The occurrence of diffusive effects ensures that solutions are always smooth. So, smoothness of the solution, like we saw in the case of elliptic equations, occurs even over here. And that happens even if you have initial conditions which contain discontinuities. For example, in this problem, at t equal to 0 plus, suddenly there was a jump in the velocity at the upper wall. So, you may consider that to be a discontinuous change, but irrespective of that, the solution in the interior domain remained smooth. The steady state is reached after a long time and the equation then displays elliptic behavior. So, that is what we saw over here, that as t tends to infinity, asymptotically a steady state solution will be generated which has an elliptic behavior. Let us discuss hyperbolic partial differential equations. So, they dominate wave propagation and vibration problems, and they are associated with negligible energy dissipation. However, dissipation was seen or diffusion was seen in the case of parabolic partial differential equations. For example, the linear advection or linear wave equation that we have studied earlier is a non-dissipative wave propagation equation, and therefore, the wave amplitude that we define as an initial condition at t equal to 0, that propagates through the domain in an unattenuated manner. Hyperbolic problems like parabolic partial problems are also initial boundary value problems. Discontinuities can be accommodated by these equations. Examples of them are shock waves. So, in the solution domain there could be discontinuities, unlike what we saw in parabolic partial differential equations, that the solution will always be smooth even if there are discontinuities in the boundary condition. That does not happen here. The solution itself can support discontinuities. And when you look at compressible flows for inviscid situations, they behave in a hyperbolic manner at subsonic as well as supersonic conditions. This we saw from the steady form of the velocity potential equation earlier, when we were categorizing the partial differential equations. And when we develop computational techniques for hyperbolic partial differential equations, they have to support the existence of discontinuities in the interior solution. And again, disturbances at a point can only influence a limited region in space, leading to zones of dependence and influence, which we have seen earlier. Let us say we discussed about the existence of two real characteristics which have distinguished those regions. Another very important point, the speed of disturbance propagation in a hyperbolic problem is finite. It is equal to the wave speed. You may recall that in linear wave equation we had a velocity of the wave. So, the waveform was propagating with that velocity, either towards a positive x or a negative x direction, when we were considering a one dimensional linear wave equation. However, in parabolic and elliptic equations, we see infinite propagation speeds of disturbances or informations. So, in this lecture we discussed about mathematical classification of partial differential equations in the beginning, and then we discussed how a second order partial differential equation may be categorized as either a hyperbolic, parabolic or elliptic one. Subsequently, we discussed about the physical behavior of these partial differential equations, and a numerical scheme for solving such a partial differential equation will certainly have to take care of its physical behavior. Thank you.